The Anova, or analysis of variance. Its meaning, types, examples, formula, and computations. One-way Anova, and two-way Anova. Post-hoc analysis, Tukey HSD, and Bonferroni test. The Anova, or analysis of variance, is one type of inferential, parametric, statistical tool for evaluating differences of three or more independent populations, using hypothesis testing. Anova tells how significant the differences between means of the groups are, and if differences are by chance. Anova is used when data groups follow a normal distribution, variance are assumed equal, and random sampling was used for all treatments. Anova helps you find out whether the differences between groups of data are statistically significant. It works by analyzing the levels of variance within the groups through samples taken from each of them. Here are some sample research studies applicable for analysis of variance. A steel manufacturer has 3 different processes to make steel bars. They want to know if one process is better than the others. A group of patients are trying 4 different therapies: drug, medical, nutrition, and stem cell. You want to verify if one therapy is better than the others. Students from different high schools take the same exam. You want to see if one school outperforms the others. There are 2 main types of Anova that are commonly used in many academic and professional research analysis: the one-way Anova, and the two-way Anova. The one-way Anova is a type of statistical test that compares the variance in the group means, while considering only one independent variable, or one factor only. The independent variable divides cases into several group levels, or treatments. For example, a market researcher may be interested in studying how its brand product perform with consumers when using different types of cereal. So, she can then measure their responses when the product uses wheat, maize, or rice. Take note that the data is measured based on the dependent variable, DEV, or what we call the response variable. In this case example, the dependent variable is consumer response. The two-way Anova is a type of statistical test that compares the variance in the group means, while considering 2 independent variables, or 2 factors. The 2 independent variables are still divided into several group levels, or treatments. For example, the market researcher not only wishes to determine the performance of its product based on the type of cereal. In addition, she also wanted to measure consumer response when using different amounts of calories in the cereal. So, she also used unsweetened and sweetened cereals. Again, take note that for both dependent variables or the 2 factors, the data is measured based on the same dependent variable, which is consumer response. Here's another example. A farmer wanted to test the effect of adding different amounts of magnesium on the growth of his plants. Each plant had different level of magnesium, 0, 5, 10, 15. and the plant height were measured every week for 1 month. Then, he would use Onw-Way Anova to determine if there was a statistically significant difference in the mean heights of plants, watered with the different amounts of magnesium. The independent variable is amount of magnesium. The groups or levels are 0, 5, 10, 15, and the dependent variable is the plant height. The farmer may be interested not only in seeing how different Mg levels affect growth or height, but also in studying whether or not it varies when plant is planted at locations with different soil acidity. With this additional factor, the two-way Anova would be used. In this case, the first independent variable or factor 1, and the levels, are the same as the Onw-Way Anova. The second independent variable, or factor 2, would be soil acidity. The group levels are pH 5.0, 5.5, and 6.0. The dependent variable is still the plant height. Anova measures two sources of variation in the data, and compares their relative sizes. In variation between groups, for each data value look at the difference between its group mean, and the overall mean. Next, in variation within groups. For each data value, we look at the difference between that value, and the mean of its group. This figure summarizes what needs to be calculated to perform a Onw-Way Anova. Take note, the Anova F statistic is a ratio of the between-group variation, divided by the within-group variation. Here's an illustration of how the variances affects the result. This are the variances between groups. And here are the variances within groups. Anova computes the F ratio, which equals variance between groups divided by a variance within groups. If somehow the data of the curves of three different groups changed, such that the curves are further apart, this would result to larger variances between groups of data. Since the within variance is still the same, then, this would result to a larger F ratio. A large F is evidence to reject null hypothesis, since it indicates that there is more difference between groups than within groups. If somehow the data of the curves of three different groups changed, such that the curves become broader, this would result to larger variances within the groups of data. Since the between variance is still the same, then, this would then result to a smaller F ratio. A small f is evidence to accept null hypothesis, since it indicates that there is more difference within groups than between groups. Let's have some sample problems on Onw-Way Anova analysis. A medical researcher has 25 patients with blisters. She wants to determine the effect of treatments A, B, and P to the healing time of their blisters. The measurement data from the different treatment groups are shown. The mean for each treatment group are also given. What we need to know is whether the means of the groups are significantly different from each other. The null hypothesis here states, the means of all the groups are equal. The alternate hypothesis, not all the means are equal. This figure illustrates the side-by-side box plots, or box and whiskers plot, of the data for the three treatment groups. At a glance, this box plots gives us an idea, or clue, of how far away or different the group data are from the other group data. Here is the output of the Anova analysis of data from the three different treatments on blisters, using a software application. Take note, the manual computation of Anova, though long and tedious, would yield the same results. From the Anova software output, notice that the table result includes the degree of freedom for groups or treatments, which is 2, the degree of freedom for error, which is 22, and the total, which is 24. Also, we can see the sum of squares groups, SSG, or sum of squares between. The sum of squares error, SSE, or sum of squares within. And the sum of squares total, SST. Also, we notice the mean squared variation due to groups, MSG, mean squared error, MSE, the F ratio, or F statistic, and the p-value. Since we need the F critical value, let's use the F distribution table. Look for the degrees of freedom of 2, at the top columns. Then the degrees of freedom of 22, at the side rows. Notice that the intersection is at 3.4434, which is the critical F value. Let's make the decision. Since the F value, 6.45, is greater than F critical, 3.4434, we reject the null hypothesis. Then we can say, there is a significant difference between the means of treatment groups, A, B, and P. An alternative decision is, since the p-value, 0.006, is less than significance level, 0.05, then we can say, there is a significant difference between the means of treatment groups A, B, and P. However, this Anova result does not tell you which group means are significantly different from other group means. Thus, we need to do post-hoc analysis. Once Anova indicates that the groups do not all have the same means, we can compare them 2 by 2, using the multiple two-sample t-tests. These multiple comparisons tests are termed post-hoc analysis. During post-hoc analysis, we need to adjust our p-value threshold, because we are doing multiple tests with the same data, and minimize the probability of a type 1 error. There are several methods for doing this. Examples are the Tukey HSD, and the Bonferroni test. Here is the result output from Tukey HSD post-hoc analysis on application software, with p-value results for groups A, B, and P. Please notice that only treatment A and P are significantly different from each other. The Bonferroni test post-hoc analysis is the simplest post-hoc multiple comparisons test. In this statistical analysis, a series of t-tests are performed on each pair of groups. To avoid inflating the type 1 error, the significance level, 0.05, is divided by the number of comparisons, or testing pairs. This is Bonferroni correction. In this case, the new critical p-value is 0.05 divided by 3. This equals 0.0167. Again, please notice that only treatment A and P, the placebo, are significantly different from each other. Thus, we can also conclude that treatment A is the effective treatment. Let's have an example for the two-way Anova. An agricultural researcher wants to know the effect of sunlight exposure and watering frequency in plant growth. He planted 40 seeds and allowed them to grow for 2 months, under 2 different conditions, which are sunlight exposure and watering frequency. For the first factor, the treatment levels, or conditions, are none, low, medium, and high. For the second factor, the treatment levels, or conditions, are daily and weekly. After 2 months, plant height is measured. Here is the tabular results, when the researcher measured the height of each plant. The means of data, for each group, were also computed, and presented. For this two-way Anova, we will have 3 sets of hypotheses. For the factor 1, sunlight exposure. For factor 2, watering frequency. And last, for the interaction of both factors. This is the two-way Anova result using an application software. Let's consider, and focus, on the p-value results. The p-value for interaction, 0.310898, is greater than 0.05. This is not statistically significant. The p-value for watering frequency, 0.975975, is greater than 0.05. This is also not statistically significant. The p-value for sunlight exposure, 0.00000039, is less than 0.05. This is statistically significant. Thus, from the p-value results of the two-way Anova, we can infer that only sunlight exposure has a statistically significant effect on plant growth. We had previously determined that there is a significant difference in the means of groups in the sunlight exposure factor. However, Anova does not tell which group is different. Here are the means for each group, and their graph. Which mean of each group is statistically different from the other. Also, notice that the mean of group C has the highest value. Can we conclude that group C has the best result? Statistically? Not yet, of course. To verify this, we can use post hoc tests, like Tukey HSD, or Bonferroni test. Let's use the Bonferroni test for the post hoc analysis. In this case, The new critical p-value is 0.05 divided by 6 comparisons. This equals 0.0083. After computations, here are the results of the p-values per testing pair. Please notice that there is a significant difference in the testing pair AC and pair BC, but not significant for pair CD. This means that only group C with medium sunlight exposure provides the optimal condition, with statistically best results, on plant growth.